Okay, today we're going to talk about the periodic table a little more. So we're still in chapter 4. Charged states of particular elements based on where they are on the table. I'm going to talk about periodic table trends. Oops, make that a little more legible. And finally, I'm going to talk about isotopes and average mass calculations. Yeah. Just going to give everyone a couple more seconds to write this down. Okay. So I'm going to go to my periodic table, have your periodic table out to write on if you have it, and Chris will bring more for the people who don't have them right now. Let's see. Here we go. Here's the periodic table. On Wednesday, we learned that as you go down the periodic table, what happens? What happens as you go from one row to the next? Anybody remember? What do you add? An orbital level or an n level, right? So for row 1, you it's n equals 1 orbital, and then 1 orbital level, and then as you go out down to row 2, you have another orbital level, and so on. Now, the outermost orbital level is called the valence shell, the valence electron shell. And so, for example, with n equals 1, the only shell present is the valence shell because that's the outermost. However, when you go to n equals 2, you have an outer shell and an inner shell. So that outer shell, that n equals 2, is your valence shell. However, we didn't talk about what happens as you go across the periodic table. What happens when you go across the periodic table is you're actually filling those shells with electrons. And so the number of elements across the table actually tells you how many electrons can fit in that n level, in that orbital shell. So, for example, in n equals 1, we can only have 2 electrons because hydrogen and then helium, that's it. So hydrogen has 1 electron and helium has 2 electrons when they're neutral, okay? How many electrons can go in our n equals 2 shell? Based on how many elements there are across the table? 8, right? Because as you count across, 1, 2, 3, 4, 5, 6, 7, 8, which means that lithium has 1 valence electron, so it has a full n equals 1 shell, and then it has to go to the next shell. and we have one valence electron, one outer electron in lithium. Beryllium has 2 outer electrons. Boron has 3, and so on to neon, which has 8. Okay, so you're filling that outermost shell as you go across the table. And the outermost electrons are the ones that can be given or taken away, right? They can be the outermost valence, those valence electrons are the ones that are exchanged when atoms gain or lose electrons. We're going to focus a lot on the first 3 N levels. And the reason for that is that those are all main group elements. You'll see, so there's transition metals, but in N equals 1 through 3, there's only main group elements, this and that. Can you raise your hand if you do not have a periodic table? Keep it raised. The great thing about N equals 1 or N equals 2 and N equals 3 is that this 1A through 8A column label, it tells you how many valence electrons that element has. So for example, boron is, you count across 1, 2, 3 valence electrons, it's in group 3A. So how many valence electrons does oxygen have? 6, because it's in 6A. And then you go all the way to 8A, and those noble gases have that full valence shell. So the noble gases over here, this means that they have a full valence shell. And a full valence shell means that they are very stable. I won't talk about the quantum theory of that stability. I'll just say that they're having a full shell means you're low energy, and you want to be low energy. Just like you're sitting right now, you don't stand for an hour and a half to listen to me talk because that takes energy, right? You want to be in a more stable position. You want to be lower energy. You're happier there sitting versus standing through the whole class. Atoms are the same way. They want to be low energy. They want to be stable. And the way you get to be stable, the most stable, is that you have an outer shell of electrons that is full. Does anybody know what it's called when, for example, if you are in here and you have a full 8 electrons? It's called a full. Anyone heard this before? Full octet. These elements have a full octet because they're in group 8A, and as you fill across, you have 8 electrons in the valence shell. You have a full octet. Okay, so other elements want to be like the noble gases. They want to be stable. They want to have a full octet. They want to have a full valence shell. And the more neutral, so the more stable a neutral element is, the less likely it is to react. Which is why, does anybody know the other name for the noble gases? No? Inert gases? So inert means you don't react. And because these elements are very stable in their neutral state, which is where they have the same amount of protons and electrons, they're not going to react, they're not going to gain or lose electrons. However, other elements who want to gain and lose electrons do tend to react, and we'll talk about that. So they're going to gain, other elements are going to gain and lose electrons in order to be stable like the noble gases. Take, for example, fluorine, upper right corner right here. Fluorine has how many valence electrons? 7. So how many electrons does it need to gain to have a full octet? 1. So it's going to really want to gain an electron, and it's going to become F minus, because if you gain a negative charge, you are going to be positive. I mean negative, sorry. If you gain a negative charge, you are going to become more negative, okay? And actually this is true down this whole group. All of these want to have a full valence shell, so they're all going to try to gain one electron, which means that the most likely charge on this group 7A on the halogens is -1. Okay, so this is what you should put on your periodic table. You need to remember that halogens will have a -1 charge. Now, how many electrons does sulfur need to gain to have a full octet? 2. Yeah, because it's in 6A, it needs 2 electrons. So it's going to become, and so instead of neutral sulfur, it's going to gain 2 electrons because it now has 2 more electrons than protons. And it's going to become S2 minus. And that's going to be true for all of group 6A. So that charge is going to be -2. What do you think the charge on 5A is going to be? -3. We're going to actually now move to the other side of the periodic table. Let's talk about sodium. Sodium has 1 valence electron. It has a whole new shell with 1 electron in it. I'm going to move this chair. I keep tripping over it. That's incredibly energetically unstable. It doesn't like having that. That is like a company building a whole new floor for 1 employee, right? It doesn't, for a company, it's not cost effective. For sodium, it's not energy effective. So what that company would do is that company would figure out another place to put that employee, or they just get rid of that employee, okay? They'd kick them out, because building a whole new floor for 1 employee doesn't make any sense. Sodium's going to do the same thing. Sodium is going to kick out that electron, so it doesn't have to have a whole new shell for 1 electron. Now, you could say, well, sodium could gain 7 electrons for a full octet instead of losing 1, but that's a whole lot more work than just kicking out 1 electron, okay? So if you lose 1 electron, what's your charge going to be? +1. Because you're losing a negative charge, you become positive. So that's going to be Na plus. So that whole row is going to have a +1 charge. I mean, so the whole group, yes. So this whole, all of the alkali metals will form a +1 charge. Can you tell me what you think beryllium and the other alkali earth metals, what charge they would have? +2. What about boron and all of these guys? +3. Because it's much easier to lose 3 electrons than gain 5 more for a full octet. Any questions on this? Yeah, it's like a divide, right? The divide is for A. And you'll notice that I haven't given a charge for group 4A. And that's because it's right in the middle. Group 4A doesn't tend to form charged particles. 4A, we'll learn later what a covalent bond. Group 4A tends to share electrons versus giving them away or taking them. Okay, so you don't have to know the charge for 4A, but you do have to know all of the others, including what is the most likely charge for the noble gases? Neutral, because it doesn't want to lose or gain electrons, so it's going to be 0. So you have to know the charges for each of the groups, 1A through 3A and 5A through 8A. You have to know those. Can anyone tell me what a charged atom is called? So a positively charged particle is a cation. In general, a particle with a charge is called an ion. So an ion is a charged particle. This could be a charged molecule or a charged atom. Right now, we're just talking about charged atoms, right? We're just talking about boron, which is neutral, loses 3 electrons and becomes boron 3+. Now, a cation is a positively charged particle, ion. So a positive ion. So the cations we have here are the alkali metals, the alkali earth metals, and group 3A. And then you also have anions are negative ions. So those are groups 5A through 7A. Negative ion. There are multiple ways to remember these terms. You can remember that cation has a T in it. T looks like a plus. Plus is positive. You can also remember that cats have paws. Cation is positive. There are also people who are like, well, I like cats, so cats are positive. I don't like cats, so that doesn't work for me. I'm definitely a dog person. So I just remember that cation has a T in it. That's a plus sign. Anion, if you're anti on an issue, you're negative on that issue. Okay, so anion, negative ion, cation, positive ion. The closer an element is to having a full octet, the more reactive it is going to be. So the halogens are pretty reactive because they really want to get that extra electron. They are so close, they're pretty unstable. They want that final electron. Now the alkali metals are even more unstable because they've got that full valence shell that they want to get rid of. They want to get rid of that that one extra electron. So what the neutral alkali metal is going to do is it's going to react really explosively to get rid of that electron. So the more atom wants to get rid of or gain an electron, the quicker it's going to react and the more explosive it's going to be. So we're going to watch a video of neutral alkali metals being thrown into water. So this is going down, we're going to go down the periodic table. We're going to start with lithium. It's an alkali metal. You put lithium in water and it sets on fire. Sodium's going to be even a little more reactive. And this is just them being put into water. That's how reactive this is. This happens just in water. And then they're going to show this in slow motion. This is one drop of water reacting with a chunk of sodium metal. So very, very reactive. And this next experiment I would not recommend doing. So that's a big piece, that's like a brick-sized piece of sodium that they threw in a lake. And rubidium actually, yeah, so this can completely shatter a bathtub if you put rubidium in water. So it completely broke the container it was in, and they're gonna show it in a bathtub again. Francium is incredibly unstable. We don't have enough francium to chunk of it to throw in water. This is their illustration of how reactive francium would be if you threw it in the ocean. Does anyone know what that actually is? It's an atomic bomb in the ocean with like a battleship in for scale. So who knows if francium would actually create, but it would create a pretty big explosion. So as you go down the periodic table, the alkali metals become even more reactive. And they actually have to store alkali metals in oil because they don't tend to react with oil, but they do tend to react with water. So because water and oil don't mix, if you store like a sodium in oil, the water won't be able to reach it and react with it. Okay, so that's our video. All right, and that video is available under Fun Stuff, Darth Vader. All of the videos that I show you in class, plus a few more, will be, so if you're listening in from home right now, that video is under Darth Vader. So yeah, all of the videos that I show in class are uploaded online under Fun Stuff. You might be wondering what happens with the transition metals. The transition metals have more complicated orbital dynamics, so you don't have to memorize their charges because they can have multiple charges, and that'll factor in next week when we start naming compounds and putting them together. But transition metals can have multiple charges, most of them can, and you don't have to memorize those. So the only charges you have to memorize are 1A, 2A, 3A, 5A, 6A, 7A, 8A. Questions? All right, let's talk about periodic trends. I'm going to get rid of this. I'm going to go back to my whiteboard because I don't need to talk about specific elements. I'm just going to draw a periodic table here for you, just kind of the outline, because I'm just going to talk about trends. Okay, here's my table. So as we go down the periodic table, I mentioned that we add valence shells. So what do you think happens to the size of the atoms as you go down, the elemental atoms as you go down the periodic table? They get larger. That makes sense. So the size trend increases as you go down and to the left. And I'll explain why. Let me actually, I'm going to redraw that to be a little bigger. Okay. So the periodic trend for size is it increases as you go down and to the left. Now, going down makes sense, but you're also might be wondering why, for example, it gets smaller as it goes to the right, because aren't you adding more electrons in each orbital? You're also adding more protons to the nucleus as you go across the table, right? So as you're adding electrons in a neutral element to make the element neutral, you also, as you change the element, you are also adding protons, right? Because change the proton, you change the element. So as you go across the table to the right, you're going to have a really highly concentrated positive charge, and that in the nucleus, and that positive charge is going to get more and more positive as you add protons. So the electrons that are surrounding it get pulled in a little closer, which means that the smallest, one of the smallest atoms is fluorine. Fluorine is very, very small. It's top and to the right. You know, helium is even smaller, but as you're top and to the right, you only have 1 or 2 valence shells, and they're being pulled in very much by the protons in the nucleus. Francium is one of the biggest elements, and that's because it has the most valence, it has the most orbital shells, right? It's got 7 orbital shells, and it's only got one, as you're going across, it's got that 1 electron, and that electron doesn't feel the pull of the nucleus as much. So it's just a bigger element. So what you need to know is just size increases down and to the left. Electronegativity, which I will define electronegativity, has the opposite trend. So electronegativity, which can also be abbreviated as EN, is the likelihood that an element will gain an electron. I also call it kind of greediness for electrons. This makes sense, right? Because we just saw francium theoretically react very, very strongly to get rid of an electron. So if it's trying so hard to get rid of an electron, it's not going to try. It's going to be the least likely element to try to gain an electron. Fluorine, however, is in that the electronegativity trend doesn't include the noble gases because those don't want to lose or gain electrons. So fluorine is the most electronegative element because it is in the halogens. It's in group 7A. It really wants that final electron to have a full octet. It's also very small, which means that when that electron is coming in, it can really feel the pull of that nucleus, okay? So because of that size, it's going to really, fluorine, it's gonna really feel the pull of that nucleus, and that other electron is really gonna wanna attach to fluorine. So fluorine is the most electronegative element. For your purposes, just know that the trends are opposite. Electronegativity increases up and to the right, and size increases down and to the left. Questions on that? If you go on into 110, you will learn kind of the some of the quantum mechanics behind those trends. Let's talk about isotopes and average mass. Does anyone know what an isotope is? I kind of mentioned it on Wednesday. Yeah. Atoms of the same element, so same number of protons, that have different number of neutrons and therefore different what? AMU, yes, mass. So remember, protons affect what? Number of protons determines what? Element. Number of neutrons affects mass. Number of electrons affects charge. Beautiful, never forget. So we have different symbols, right? So for example, sodium, that's the atomic symbol. Na plus, sodium plus, is the ionic symbol. Now I'm going to show you what an isotopic symbol is. okay? So do know when I say, okay, what I'm asking for when I ask for the atomic, ionic versus isotopic symbol. So an isotopic symbol has a few elements. First, you have, and I'm just putting in, so X is just any letter, any atomic symbol from the periodic table. So it could be B for boron, it could be Xe for xenon. So that's the atomic symbol. Yeah, what's up? Ionic. I-O-N-I-C. Mm-hmm. Yeah, that does look like an M, doesn't it? Ionic. Yeah. So in the isotopic symbol, just like in these two guys, you have the atomic symbol, right? This is Na and that's Na. But you also have the mass number. So you have, I'll just put in A for mass number. And mass number, does anybody know what that is? Protons plus neutrons. And finally, we have our atomic number, which is optional. In our isotopic symbol. Can anyone tell me why our atomic number is optional? How do you already know what the atomic number is? If you look at the periodic table and you look at this symbol, you know what the atomic number is, okay? So you can not include that, that's optional. So I'll give you examples of the three ways I accept isotopic symbols. Does everybody have the sound, or do you need a couple more minutes? Okay, it looks like a few people are still writing. An example would be carbon 12. So you have the atomic symbol, the atomic number, and you have the mass number. Based on the mass number, how many neutrons do you have? 6. Because the number 12 is the protons plus the neutrons, 6 is our number of protons, so 12 minus 6 is 6 neutrons. I would also accept you write it this way without the 6, because once again, if you look at the periodic table, you know that carbon has 6 protons. And finally, I will also accept C12, C-12. This you will, if you go on in the sciences, you might see in literature. So I want you to be able to identify that as an isotopic symbol as well. Another example of, so a different isotope of carbon, you could write it these 3 ways, is carbon 14. Now, how many neutrons does carbon 14 have? 8. Because 14 is equal to 6 protons plus a number of neutrons. 14 minus 6 equals 8. 8 neutrons. Yes.
And you know that because of just looking at the periodic table?
Yeah.
And then other ones we should have memorized, correct?
In terms of how many protons you have?
Yeah.
No, you don't have to memorize, because you will have this table on the test. Okay. You just won't have the names. So it'll be everything on this except for whatever you've written. Okay? So when you look at the periodic table, you can see that carbon, but you have to be able to identify it as carbon, right? Versus, chromium, right? C is carbon, Cr is chromium. Yeah, so you have to know the name of carbon, but you don't have to have the number memorized because you'll have it on your table. So 12 is the mass number. So 12 is equal to 6 protons plus some number of neutrons, right? So when you subtract 6 protons from the mass number, you get 6 neutrons, which is why, so 6 neutrons. So then if you do the same thing for C14, 14 equals 6 protons plus however many neutrons. If you subtract 6 from 14, that means you have 8 neutrons in carbon 14. So the number of protons never changes, which is why this number is optional, but the number of neutrons can change, and that determines our mass number, how much our isotope weighs. Any other questions on this? All right. Let's talk about how to determine your average atomic mass. Have you ever calculated your grade in a class where different assignments have different weights? That's essentially what we're going to be doing. We're going to be doing a weighted average. So for example, if you calculated your grade for this class, you would say, well, my first test was worth 8%. My second test was worth 10%. So you turn those percentages into decimals, and you do 0.1 times your grade on the second test and 0.08 times your grade on the first test. And that would give your test average, okay? So that's the same way we do our average atomic mass, which is how we get those atomic masses on the periodic table. I said on Wednesday that the mass on the periodic table is the average atomic mass, which is the average of all naturally occurring atoms of that element I would say on Earth, because I don't know if we're sure the distribution in our universe. So for example, carbon, it's mostly C12, but there is some C13 and some C14. So our average atomic mass is not exactly 12, it's 12.011 because we have a few heavier atoms out there. Now let's talk about how to calculate that. Average atomic mass is equal to the decimal of isotope 1 times the mass of isotope 1. That's plus the decimal of isotope 2 times the mass of isotope 2. Spelled isotope 2 wrong, but that's okay. And so on with however many isotopes you have. Most of our calculations will just involve 2 or 3 isotopes. But you could have as many isotopes if you wanted. If you had a lot of different isotopes of a particular element that were significant in contributing to the mass, you could have a great number. But this is the general layout of this formula, and then I'll give you an example in number form. When I say decimal, I'm talking about the decimal form of the percentage, which how do you convert a percentage to decimal form? Divide by 100. Okay, so the decimal is equal to the percentage of that isotope's abundance. So basically, what percentage of the isotopes in the world are that weight divided by 100. So for example, if I said 50% of copper was copper 63, my decimal would be 0.5. I could say, so for example, chlorine is 75.77% chlorine 35, which weighs 34.97 AMU. Remember how I said that protons and neutrons don't weigh exactly 1 AMU? That's where this factors in. So it's chlorine 35, which is your mass number because that's number of protons and neutrons. So that's just to the one place. But if you took it out further, it would be slightly off of that mass. So just be prepared for the fact that your mass of chlorine 35 will be very close to chlorine 35, but not exactly. The other 24.93% of chlorine is chlorine 37, which weighs 36.97 AMU. What is the atomic mass? And in this case, I'm talking about average atomic mass. We're going to take these numbers and we're going to put them into this equation. So what's my decimal of isotope 1? 0.7577. And we're multiplying that by 34.97. So our isotope 1 is chlorine 35. Our isotope 2 is chlorine 37. So we're gonna, our next part is 0.2493 times the mass of chlorine 37, which is 36.97. And when you do the math, you should get 35.45 AMU. And you do have to watch your sig figs on this question. And so you got a number that matches the periodic table. However, I will not always give you the real numbers because I don't want you to be able to check your answer by looking at the periodic table. So sometimes the answer that I give you will be slightly off from the periodic table because I want to make sure you actually knew how to do the math that is involved in finding the average atomic mass. So here I gave you an answer that will give you the exact mass of chlorine, average atomic mass of chlorine, but sometimes it'll be slightly off. So don't worry if your answer is slightly off from the periodic table.
And this is the answer you'd want. You wouldn't say like have to add chlorine to the the box answer to make it clear.
No, as long as you have the units. Yeah. Yeah, that would be fine. Yeah. Yeah, you know what, it is supposed to be 24.23. You are right. So because I had that written wrong in my notebook, and that happened last night too. There we go. 24. That should give you the right answer. If you were confused as to why you were getting the wrong answer, that's why I wrote down the wrong thing. because 100 minus 75.77 is not 24.93. Thank you for pointing that out. Can you do one on your own? Okay, Chris and I are here to help, but let's do 69.17% of naturally occurring copper is copper 63, which weighs 62.9395 AMU. The rest of naturally occurring copper is Cu65, which weighs 9278. What is the atomic mass? Can anyone tell me, there's a piece of information that I did not give you, but you have enough information to figure it out. What? Yeah. I didn't give you the percentage of copper 65, but assuming these are the only two isotopes, I said the rest. So what do your percentages have to add up to? 100. So your percentage of copper 65 will just be 100 minus 69.17. So you have to do that first and then put it into your equation. Sorry, what? Yes. Depending, so it's 5, but depending on rounding, if they round first, it can be 6. Yeah, either one is fine.
For the periodic tables, I didn't have blank ones.
Oh, that's fine. Yeah. Actually, so yeah, the people who got the periodic tables from Chris, you actually have all the notes.
Just need to recolor it.
Yeah, just if you want to color it.
It's
It's like, give me attitude.
Oh, here you go, Ben. Today's your lucky day.
Yeah.
Too late. There you are.
Thank you.
Those who seek get.
Close off on that, huh? Yeah.
But still make sure you watch that lecture. You should watch it. Let me walk through this. So first, let's turn these percentages into decimals. So 69.17 divided by 100 equals 0.6917, and that's the decimal of copper 63. And what did you get for the percentage of copper 65? 30.83. So 30.83 or 30.38? 83? Okay. Divided by 100 equals 0.3083. Okay, so those are your decimals. And I'm going to put in, so 0.6917 times the mass of isotope 1, which is copper 63, 62.9395, plus 0.3083 times the mass of the other one, which is 64.9278. Make sure you assign the correct percentage to the correct mass. Okay. I'm gonna do this. I'm gonna show decimals. I mean sig figs. So I'm gonna do it step by step. So first I'm gonna do the multiplication, and then I'll do the addition. The first one is So 0.6917 times 62.9395 gives you 43.5352. How many sig figs do we have for just that part? 4, because 0.6917 has 4 sig figs. So it's going to be specific to the hundredths place. And then we're going to do the same for the other part, 0.3083 times 64.9278 gives you 20.0172. And how many sig figs there? 4, because 0.3083 has 4 sig figs. So your answer now is going to be, when you add, they're both specific to the hundredths place. So your answer will be specific to the hundredths place. 43.5352. So depending on how you rounded, it will be 63.55 or 63.56. AMU. Always include your unit. Questions, concerns? Okay. I think the main sticking point for that one is sig figs. Now let's talk about if I give you the average mass, but I don't give you the percentages, and I ask you to find the average, the percent abundances of 2 different isotopes. All right, everyone has this down? So I could say that the mass for carbon 12 is 12.000 AMU, and the mass for carbon 13 is 13.003 AMU. And the average atomic mass for carbon is 12.011 AMU. What is the percent abundance of carbon 12, assuming all other isotopes are negligible? So write this down and then we'll talk about how I would work through it. And that's a C13, carbon 13 at the top. You may think that you don't have enough information for this. You do. So let's just write it out as, I'm just gonna put in variables right now. So X is the decimal for C12 and Y is decimal for C13, okay? So because we don't know the percentages, we don't know the decimals, so we're just gonna put those in as variables. So X times 12.000 plus Y times 13.003 equals 12.011, because that's our formula. Decimal of isotope 1 times mass of isotope 1 plus decimal of isotope 2 times mass of isotope 2 equals the average atomic mass. We just have to figure out what X and Y are. Since we only have 2 isotopes, what do their percentages add up to? 100, which means their decimals add up to 1. So your X plus Y equals 1. You now have a 2-variable, 2-equation system. Do you remember how to solve these? Solve for 1 variable and substitute? Yeah, so I'm going to solve for Y. So y is going to be equal to, so I'm going to subtract x from this side. Y is equal to 1 minus x, right? So I'm just subtracting, I'm solving for y right here, and it's equal to 1 minus x, and then I'm going to substitute it in. So this is now going to be substituted in for y, which means that 12 times 12 point x times 12.000 plus 1 minus x times 13.003 equals 12.01. You now have one equation and one variable. You can solve for x. What do we have to do to solve for x? Distribute. Okay, so 12.000x plus 13.003, right? Because 13.003 times 1 is just 13.003 minus 13.003x, right? Because I just distributed that, equals 12.01. Now I'm going to try to get the x values and the non-x values on the side. So here I'm going to combine these two x values, subtract 13.003 from 12, and then subtract 13.003 from both sides to get the non-x values on the right, which will give us negative 1.003x equals negative 0.992. When you solve for x, you get x equals 0.989 because we have 3 significs. What does this mean? It's a percent of what? So that's a decimal of what? C12. Yeah, because x is what we multiplied by carbon 12 initially. So if that's a decimal of carbon 12, what's the percentage of carbon 12? 98.9. So carbon 12 is 98.9%. And that's your answer. I may ask for the other isotope, so then you'd have to solve for the other one. So if I asked for carbon 14, what would you do then? Subtract it from 100. Yeah, it would be the remaining percentage. Any questions on this? I'm going to give you one to do yourselves. I'm going to wait for everyone to write this down, and then I'll give you an example. And we are perfectly on time. 15 minutes. Yeah, it is. Alrighty. Does anyone know what S is? Nice. You've been studying your solve for the percent abundance of sulfur. There are 2 ways you can do it. Do it the way that makes sense to you. Yeah, but what times? Yeah, yeah, there you go. That would make a lot more sense.
Yeah.
Yeah, but you actually want to.
No, I missed it.
No, it's right, but wrong number 6. Well, look how many six you have here. I'm gonna do it the other way where you get 3, but yeah. So because you have 2 sixes here. All right. Did it? You should have 2 or 3 sig figs. The way I'm gonna do it, it's gonna have 3 sig figs because you can either solve for y first and substitute that, or you can solve for x first and substitute that. Depending on which way you did it, you might. But on the test, I will tell my graders that that either is correct. Okay, I'm gonna solve for y and then substitute in. So that is, so first I'm gonna do 31.972 times x, right? Because we don't know x, plus 33.968 times y equals 32.065. Now, once again, x plus y, the percentages are equal to 100%, so their decimals are equal to 1%. I mean 1. So x plus y equals 1. Solve for y and plug that in. 31.972x plus 33.968 minus 33.968x equals 32.065. This will give you negative 1.996x equals negative 1.903. And x is going to equal 0.9534. But because I solve for x, this is the decimal for 32. I need the decimal for 34. So instead of 95.34%, that's 32s, it's 100 minus that, which is 4.66. If you just went and you solved for x here and you plugged 1 minus y in, you would have gotten 2 sig figs, so your answer would be 4.7%. Questions? So always be careful as to which answer, which decimal applies to which number. I will see you all on Monday. You can stay a little longer if you need help figuring out. Yes.
Go with it and find it.
What did I do wrong on this one? Yeah.
Did you do, you were given, did you convert it to Celsius and then convert each individual one to Fahrenheit? I don't know. Because you didn't show a lot of work.
Yeah.
And so potentially there's a calculator error in there. And
Cool.
the grader can see what happened. If I was to guess.
Thanks, buddy.
Yeah, so this one would be more.
Yeah.
So yeah, I understand that like, but like, oh, this whole.
I have a concept question for you.
So I
Yeah.
understand why.
Okay. Why was it cool? And your word was, what was it? 31, 972, 33.968. I said you entered in the
It was
calculator.
just error in your calculator, but let's, when we do the division, this is one.
Show every step data in your calculator. That looks like one number like in the hundreds for the 10th place just got entered incorrectly, which is why I got 0.944, not 0.9524.
So it looks like God. I'm not sure. And so I'm thinking that maybe you've done one off the rounding, one off the distance, but your. I'll give you one.
Interesting.
I just got. Oh no, it's five. Yeah, it's 5 out of 6. Yeah, that's correct. You got mine.
33.065 minus 33.968
That's yes, that's
and 31.972.
so yeah, no, those other ones, yeah, I understand, like, because you're unit, you think of right units, but it has to be here
0.95.
that you actually.
Crazy.
I think that's it.
Okay.
Because the copier is like, you had it all correctly, but you just like the wrong number.
I don't know. Okay.
They're looking at office hours and on.
Do you at least understand the main concept of how to solve these?
Yes, what's the last
Yeah.
name?
I'll see you later.
See ya.